Hello. Wow, this is, I find it much more intimidating here than the other conferences because this is for developers, a lot of developers here. My marketing team helped put together the slides, so that's my first excuse. But they also went very light on the slides so that we could leave it more as a discussion. I do want this to be interesting, so don't hesitate to raise your hand if you have questions along the way. I don't mind. We have 40 minutes that you guys have apparently decided to come in and listen to me. So thank you for taking that time. And let's kind of jump in. I want to maybe try to make this a little interesting by telling the story. I had been in the HPC world, outfit by the name of Linux Networks. Any of you guys remember those guys, Alta Technologies back in the day? And had the privilege of deploying some of the first InfiniBand-based large-scale clusters for the likes of Los Alamos and Lawrence Livermore and the national labs back when InfiniBand was new. And then I came across an opportunity and built an embedded device that used Flash. And it was the contrast to the kind of, we had these clusters that used the Opteron back then, dual socket Opterons with 8 cores, and yet this embedded system with a 300 megahertz PowerPC processor running Linux, but directly from a flash chip, was much more responsive. And that kind of led to the idea of, well, how do we integrate Flash in a way that can get really high performance? And the founding of Fusion.io on that principle of stepping over the existing storage buses and controllers and protocols and going upstream directly into the PCI Express bus where you otherwise would have put the RAID controller or fiber channel card. And thus was kind of born this concept of that turned into, once it was standardized by the industry, to NVMe. And so it was kind of fun getting to be at the forefront of this transformation to solid state away from mechanical hard drives. And it really was the approach of stepping over or sweeping aside the stuff that had been built around mechanical drives to aggregate mechanical drives in RAID sets or in whole storage area networks that allowed Flash to truly shine. And that went from, it was quite successful. We went from first revenue to $250 million a year in less than 3 years as a company because Facebook picked it up, Microsoft, Apple, the web giants in China. And basically, it was more successful than I ever would have imagined because I thought most of the world needed a shared data model, and yet Flash on PCI Express in the servers themselves is kind of rolling back the clock away from a shared data model to a local storage model. But as it turned out, the big web properties had already abandoned shared storage systems and gone to a shared nothing scale-out model. And so for them, it was much easier to consume Flash in the server because they had very large homogeneous applications, and the sharing was done by how they sharded the databases. It was done up a layer. And down below, all they needed was something to alleviate the I/O bottleneck. They didn't need a shared data layer, a shared file system or whatnot at that layer. But the rest of the planet kind of benefits from having a shared data model. And file systems, had kind of grown from being local inside the OS to, mapping a whole set of drives in a RAID set to being embedded in the storage chassis as a NAS, but it all benefited from being very centralized and localized. So what stuck in my mind is, how are we going to solve the challenge of having data be unified across storage scattered inside of servers, or even across third-party storage systems or cloud services, or even across whole data centers, have it logically unified into a single namespace, even though it's physically distributed, and do that without sacrificing the high performance of Flash. And so when I left Fusion.io a good 10 years ago, you know, I started on the assumption that the trends that we see in the industry were only going to drive the need for more and more performance. And to tell a little bit more of the story, this was like 2013, 2014, 10 years ago. And the industry had attempted to take and bridge the two camps of how to do shared file data. We had the world of NAS that's based on NFS and standards, but not particularly known for being high performance, but it's very feature rich and very robust and very easy to use because it comes built in. And then you had the other camp of the HPC file systems that had been built to get crazy performance and scalability and be very efficient in how they get scalable performance. And those two worlds of HPC class parallel file systems and the NAS world, those two camps still exist today, and you even have new companies in each of those camps. But 15 years ago, there was, let's say, an attempt to merge those two with parallel NFS and the proposals around parallel NFS. But unfortunately, that early effort, at least at that point in time, didn't really catch on. And one could say because, well, these demand drivers hadn't arrived yet. You didn't have something that is pushing high-performance computing and the high-performance I/O needs into the mainstream. And it's really only been in the last 24 months. It seems longer, but it's really only been in the last 24 months that AI has exploded on the scene and thrust the more mainstream commercial need for high-performance I/O. Ironically, even for the big web properties, something that's been eye-opening to me is that the large web guys that are doing AI workloads, their shared nothing or database sharding-based models for how they run their websites really isn't sufficient for how you need to run AI workloads. You need a POSIX file system. You need high-performance shared data access that they didn't have before. So even the big web guys are now in need of a high-performance shared data environment. And it's because of the AI craze that's going on. Now, frankly, I think it took a lot longer than I had anticipated. When I left Fusion.io, I had assumed, okay, maybe 5 years, and the industry is going to, nature abhors a vacuum, and here you have flash devices with this awesome potential to deliver basically infinite performance compared to the mechanical drives before them. Naturally, people will find a way to consume or to need this kind of performance at a shared data level. But frankly, it didn't happen in that time frame. It's only happened thanks to AI in the last, again, 24 months. You had big data and other analytics stuff and all that sort of thing, but it wasn't really needing it at a general purpose file system level until recently. So what I did when I left Fusion.io, I was misguided in thinking that high performance file I/O was going to become needed. in the near term. It took a little longer, but that's okay because building file systems takes longer too. So it gave us time to get it built. But went and recruited the Linux kernel maintainer of the NFS stack, Trond, who's our CTO. He'll be speaking later today in a lot more detail on the stuff that's going on in the standards body. But we basically took the early parallel NFS work and introduced the NFS 4.2 spec to help fix some of the stuff that wasn't done well, and basically turn NFS into the most tricked out high-performance parallel file system on the planet, even in comparison to the HPC-built things like Lustre or GPFS. So if you imagine NFS, this is not your grandmother's NFS anymore. The whole Sun Microsystems dogma around statelessness and the attempt to add state into the protocol, which just kind of made it worse. Set all that aside, this has been designed now to be able to get the, to truly be a world-class parallel file system to address these kinds of needs. But the use of the architecture of a parallel file system is really to enable a set of additional innovations. The key difference between a traditional networked file system and a parallel file system is separation of the control plane driven through metadata from the data path. And that allows the data path to be parallel and scalable. That architectural change was really to enable us, this I should have gone through here. This is sort of depicting here how over time we move from having HPC class file systems to address the extreme workloads that are needed to where improving the world of NAS with things like NVMe over fabrics, that can help to some degree, but ultimately what is needed is to move to where you have the architecture from the parallel file system with the convenience and feature richness, having it just built in to the client of NFS. And that's what we're doing here. But the architectural difference of separating metadata from data allows us to address a second and major problem. So if the first problem is how do you get supercomputer class performance with the plug and play feature richness of enterprise NAS? That's what parallel NFS was designed to deliver, and although the early attempts didn't really achieve it, we're here to tell you now that it has been, and now that protocol is available for anybody to use. Now, Hammerspace has built our file system around that protocol, purpose-built, but over time we do expect others to build file systems that use the same NFS. The same way many different NAS vendors use regular old NFS v3, in the future there will be lots of vendors who will use parallel NFS for theirs. We just happen to be the first because we kind of had to fix and build the protocols in the first place to do it. But in truth, all of that work wasn't so much about performance. It was really about unlocking data from being localized in the storage. Because if you look today, we have a mess. And it's really for one reason. It's because the metadata, the data about the data, let's call it the identity of the data, is trapped down in with the data in the storage. What that means is we don't actually manage data. You manage storage, and you indirectly manage data by choosing to place the data into that storage. You don't even directly access the data. You access the storage system, and you ask it to get you a piece of data. In other words, the original sin, the source of all of the evils here, is the fact that the metadata is in the storage system with the data. And again, that's the defining characteristic of a parallel file system, is it separates the metadata. So what this allows you to do is basically abstract data from the storage storing it by pulling the metadata and serving it separately. So as an industry, we virtualize the compute. VMware initially with uplifting and uprooting the entire operating system and putting an operating system underneath a hypervisor. That was, say, Gen 1. And then we moved to a much more refined way to do that with containerized microservices orchestration. It's a lot lighter weight, it's finer granular, and it allows the data, or it allows the compute to be moved across the physical server infrastructure. All of this was to decouple the workload from the very systems running it. So as an industry, we've abstracted the workload from the servers running it. We did the same on the networking with software-defined networking. We've abstracted the logical network from the physical networking. And oh, by the way, it was the same architectural innovation that made that possible, separating the control plane from the data plane. There's a recurring pattern there, separation of control plane from data plane. That's what allowed software-defined networking to work. So of the three pillars of infrastructure, the compute, the networking, and the storage, as an industry, we've successfully virtualized the first two, abstracted those. But data abstracted from storage, attempts in the past have failed because the only way to do it would be to add an additional bump in the wire to mux how the data flows from the clients to the storage system to reroute it. And that kills your performance. In other words, it was the very fact that the protocols themselves assume metadata and data are combined, which limits you to having to be in the data path. And if you're going to be in the data path, you're going to kill the performance. So what I'm here to tell you today is quite a fantastical and very bold statement. It is that you can introduce an abstraction layer that separates logical data, unifying it from the physical storage infrastructure, and not only not compromise the performance, but actually unlock performance. Because now you're moving to a true parallel file system architecture with parallel access. In other words, if you do these two steps at the same time, then you can make it work. You have to take parallel file system architecture and put it into a standards-based approach, and then that can be used to decouple data from storage and allow data to be distributed across different storage systems and move freely across them. So this is the notion of a single namespace and data orchestration. This single namespace, now that you've separated metadata from data, you can solve the third problem, which is how do you render data across different data centers with very high latency between them. The industry has also failed to be able to have the same active file system served across different data centers with very high latency. In other words, the world of file storage has never really successfully breached the async barrier of being able to go truly asynchronous across sites. They've always had to live within the realm of the synchronous, a close enough area, like maybe doing metro cluster. About the best you can do is maybe 30 kilometers worth of latency. But as an industry, it has been one of the long-standing intractable problems of how to have the same namespace, the same active file system across whole data centers. And it also turns out the same architectural innovation separating metadata from the data path is the key there. Because now, with metadata separate, you can aggressively replicate it and synchronize it across many different data centers and give the appearance of having all of the data everywhere, all of the time. So it's kind of interesting that these three different intractable problems, the first being the convergence of supercomputer class performance and standards-based NAS, the second one being the ability to unify and orchestrate data across storage systems behind a single namespace, and then the third being able to stretch the namespace across entire different data centers. All three of those things are made possible fundamentally by separation of metadata from data. That then allows you to directly confront the challenges of building an eventually consistent multi-data center file system. And so that's at the heart of what Hammerspace does. There is a fourth piece, and that's the ability to incorporate existing data sets by reference. You can point Hammerspace to existing storage systems with data already in them, and we can abstract the data, allow the data to move, and do all of that without even having to wait to scan the metadata. Even the metadata scan happens in the background. So merely by setting up the pointer and pointing to it, you can then start using it. In other words, there is no need to do a data migration to get it into Hammerspace, since we are fundamentally a file system that works by pointer, that indirection between metadata. It allows us to incorporate data indirectly so that it can be done instantly. So you can point it to petabyte scale data sets in existing storage systems, bring all of those into the unified namespace, and the amount of time it takes is just how long it takes to set it up. You don't have to wait for any of the metadata to be scanned. That'll happen in the background on demand. So in the end, the way to think about it is this. Storage today, the file system, which is really serving the view of the data. Its main purpose is to present the data and to map and manage the data on the underlying media. So the file systems today exist embedded within the storage system or service. Now that might be a scale-out NAS, it might be a scale-up thing, it might be an object store, but the point is that storage system actually owns the metadata and owns the presenting of the data. And what that means is that data management is fundamentally to copy the data between these separate systems where it becomes new data and separate data. Whenever you copy the data, you're making a copy of the metadata, and so it's a different thing. The file foo here is different than the file foo there, and which one is my latest? The problem is that when you resort to copying, you have to question, well, which one is the real one? How many of you remember the Star Trek episode with Captain Kirk when he got split in the transporter? And which was the real Kirk at that point? Now that was a good Kirk and a bad Kirk, and he was the evil Kirk. But in the Next Generation, they had one where Commander Riker got cloned, identical clone, and his clone went on to live a successful life, go back to Starfleet or something like that. You have to wonder, which is the real one? The problem is when you resort to copying, you're actually making a copy of the metadata too, and they each are now independent, and they're not the same thing. So what we're proposing is that through parallel NFS, you can actually pull the file system out of the infrastructure and think of it like a stackable file system. The parallel namespace can sit on and consume storage systems of all types. Now, they might have their own file systems, but that's okay. Those just become storage nodes in the greater cluster. any questions here about this concept of, and of course when the file system's out here, now data movement can be put behind the facade of the namespace and not disrupt the ongoing access and use of data, even while the data is moving across separate storage systems. So you could say that this is really the logical conclusion of the progression that file systems have been on since the beginning. It used to be, like with DOS, disk operating system, it ran a single disk drive. And it knew how to map and manage data on the sector of the drives and present it as a namespace, to the computer. It was such an important part of the operating system that DOS was literally named after the fact that it could run the disk drive, disk operating system. Then file systems grew to where they could run lots of drives in a RAID set and maybe take advantage of volume managers to be able to run even more of them. Or maybe you put all of those drives in a big chassis over a storage network, and now you've got a SAN. Or we take the file system, and this was a major leap forward, we take the file system out of the local OS and we put it into an appliance on the network, into the storage chassis. Now you have NAS, and the birth of NetApp, Network Appliance, was putting that file system as a shared thing on the network. Then we made it so you could scale that out to many nodes, and you had scale out NAS. Then we had to dumb it down, make object storage, just so we could get to the kind of scale you need to host so many different tenants and large volumes of data in the cloud. But S3 and object storage is really it's in its name, super simple storage, simplified out a lot of the difficulties of a real file system so as to be able to get to the kind of scale. But the thing about all of those is it presumes metadata and data are combined. By separating the two, now you can have data move across all different types of storage in an environment. So let's just a little bit of detail on the stack up. At the bottom level, you have the orchestration services. I was speaking about the ability to incorporate data by reference. That's we call assimilation. You can do that read-only, so it doesn't even modify the original. You can point it to a snapshot on a file system, and then you can start writing it through Hammerspace, and it will simply mobilize the data off. Anytime you go to write to it, it'll move the copy. So think of it as copy on write. So you can clip Hammerspace on top of a snapshot to instantly make a writable clone of that snapshot. Or you can use it as an ongoing storage system, read-write, to where more data can be put on it. The ability to move data between storage systems then becomes completely transparent to the upper layers. You don't see it when data is moving. And this is one of the key innovations that went into the NFS standard, is the ability to introduce and reroute access to even live files that are being accessed. So the file could be in the process of being written, and on the back end, it can be uplifted and moved to different storage. That's really important because maybe it's growing so much that it's running out of space. So you might need to move it to rebalance it or whatnot. So data movement that is transparent to the ongoing access and driven by policy. Replication across data center, tiering down into storage, and then having all of this be driven by enhanced metadata. This would be a whole interesting area of discussion. But as soon as data movement no longer impacts the ongoing access to the data, now you can automate that movement. And so we have come up with a declarative intent model to where you express the service level objectives in the data itself. Oh, sorry, went the wrong way. Service level objectives are what drive how the data is placed and when it moves in an environment. Of course, this is NAS, so it has all of the rich features that you would expect in a NAS environment, including things like audit, antivirus, the snaps and clones, even some things that other systems don't necessarily have, like full file versioning and undelete. So it's not CDP, but basically if a file was closed and it has sat quiesced for a while and you go to modify it, then it'll keep a prior version. So think of it like automatically triggered snapshots at a file granularity. Because one of the problems with snapshots is you have to choose either to do them very frequently or to risk not snapshotting before something got lost. And that's a bad trade-off, to have to make really frequent snapshots or risk losing your users' data. This avoids that because you're basically saying independently snapshot any file that gets deleted or whenever it is opened and changed. This, by the way, happens to be a very powerful way to mitigate ransomware. It's like object lock in the object world, but here for the file system. So it has the full complement of the data services that you would expect, and at the parallel file system level, and the full set of protocols, including SMB, S3, NFS v3, although internally the system is using parallel NFS, and any Linux client can use that protocol. So let's jump in a level deeper, just to we have a group of developers here, so let's talk around the architecture. Because you've heard me talking a lot about parallel file system versus standard protocols, all of that. What does it actually mean? Well, the best way to see what it actually means is look at the life of a bit of data. This data is stored on NVMe. To get it into the GPU, if this is a NAS system, and what I've depicted here is what the Isilon, for example, has. Isilon is sort of the premier scale-out NAS. It has an internal InfiniBand network, and it has front-end protocol nodes as well as the back-end storage nodes. The data has to flow across the PCI Express bus twice to get out the NIC. Goes across the network at least 2 links. That's assuming that's a single level switch. It goes through the protocol node across the PCI Express bus twice, maybe even across the memory bus, and then across the Ethernet network over NFS v3 into the client. Now I've depicted here the assumption that this is using GPU Direct. You guys are all intimately familiar with GPU Direct and how big a deal it is to NVIDIA, because if you're using RDMA, it means the data can move from the NIC into the GPU. Of course, since they make GPUs and NICs, that's quite interesting to them of how to make it more efficient. So this takes nine retransmissions of the data. The data has to go over a bus or over a network cable 9 times to get from NVMe. Now, if it were not using GPU Direct, it would be 10. Wow, we just saved 1/10 by going GPU Direct. Now, the reason that VAST is claiming higher performance, and to some extent that's true, is they're able to use NVMe over fabrics. NVMe over fabrics gets the root complex out of the data path on the storage node. Now, VAST talks about this as a D node and this as a C node, controller node, data node. And they actually use a JBOF here. They don't use a high-end x86 CPU root complex. Because the data can flow using NVMe over fabrics, it's fairly lightweight on the root complex, and it's only 1 traversal over the bus. So they go from 9 to 8, and that's the huge innovation of what NVMe over fabrics does. So at Fusion.io, we not only pioneered what is NVMe, but we actually were the first to design and patent using RDMA buses to move the block data. Now, originally it was things like SRP, SCSI RDMA protocol, and other such, not NVMe over fabrics, but the same kind of concept of using RDMA to move the data directly so that you can get the root complex out of the way. Apparently, this is enough of an improvement that VAST is eating Isilon's lunch when it comes to going into HPC environments. That and the fact that they're using a JBOF here that lets them stack at very high density. So there are implications of getting this out of the way that you can put a lot more NVMe and more NICs in the chassis because you're not having to share that with the CPU. Any questions or commentary on this? Okay, so what is it about parallel file systems that's so magical? Well, basically, they take the function of a controller node and get it out of the data path. And the controller node's function is split between a smarter client and a separate control plane. The easiest way to say it is it moves from a world where data has to be proxied through another layer to a world where data can be routed through a sideband lookup. That look-aside lookup derives the routing information so that the client can then make the direct connections and speak directly and in parallel across many storage nodes. See here, the client makes one connection to one controller node, and that controller node is responsible for diffusing the data across the back-end storage. Here, the client is making connections in parallel to every storage node. So when I talk about how this architecture allows us to add an abstraction layer and actually increase performance, well, imagine that this here is stacked underneath, where I'm sitting on top of a Isilon or a VAST as my storage node, because at this place, all I need is NFS v3. That's what this is talking here. Well, as it turns out, you can actually get more performance through these systems by putting this in front of them, because then it allows parallel concurrent access to every controller node in parallel. Because now the client is connecting not just to one controller node, but to all of them. And the data that it talks about can be affinitized to where different controller nodes are used for different subsets of files. In other words, it gets rid of all of the crosstalk and contention, because you can say that the one controller talks about one subset of files, other controllers other subsets of files, and which one talks about which is determined by the metadata server. So this is how you can add an abstraction layer and have it unlock performance even on top of a single storage system. That would be like saying plug in VMware and have your single guest OS actually run faster. It's kind of cool. We had one of our customers, one of the largest movie studios on the planet, actually do the testing in Dell's lab on Isilon and showed that Hammerspace and this parallel NFS front end on top of Isilon as the storage node, it more than doubled the throughput to the Isilon and had much higher metadata performance. So they basically said, didn't matter the workload. Metadata intensive, data intensive, read, write, IOPS, bandwidth, all of those were significantly improved by having a parallel file system front end to the scale-out NAS. Now, of course, the more interesting thing is you don't need scale-out NAS at that point. You can just use traditional standalone NFS servers. You can use the NFS server that's built into Linux. So the net result of this architectural approach is that as you look at scaling performance, as you add, if you're willing to add a bunch of hardware, well, number one, here I have to add 2 layers of servers. For every unit of bandwidth I get delivered, I have to have, how many times? I have to have a NIC here, a NIC here, a NIC here, it's right, a lot. What that means is that due to the crosstalk and contention, is my clicker not working? There we go. At some point, scale-out NAS taps out. Maybe it can get to 50, maybe 100 storage nodes before adding additional storage nodes and protocol nodes doesn't really scale performance. But with a parallel file system, you can literally go to thousands of storage nodes and get perfectly linear aggregate performance across them. And so let me use a customer example here. Okay, how much time do we have left? Oh, I didn't even see it. Yeah. I went right through, sorry. So here we have an example with Meta in training of Llama, where they were able to aggregate 1,000 Linux servers with the separate control plane. And that was basically, yeah, the point of the discussion is to get here. So we leave any time at all for questions, or I ran out? Didn't see the clock.
Thank you, David. Appreciate it.
Yes.